go ahead and be here. I'm gonna, is this good or do you need the lights off?
Lights off would be good.
Some of the lights off. What are you looking at? What do you think you're looking at?
Eclipse.
An eclipse.
Astonomy.
Okay. This is called an annular eclipse, not because it's annual, but there's this ring around it. So what are you saying?
Moon covering the sun.
Yeah, so we've got the shadow of the moon, and we've got this partial view of the sun. Why don't we see more of the sun? How could we see more of the sun in an eclipse?
Where you're looking at it from, your position on the Earth.
Okay. Say that one more time. Maybe I didn't hear you right.
The position you are on the Earth.
Okay, so like, are you thinking like if it wasn't a total eclipse?
Yeah.
Okay. I guess what I'm asking is how can we make this ring bigger? Do all eclipses look like that?
Well, if the moon was a little closer. Or
Okay.
further.
So if the moon was closer to the sun, actually, we would see no ring. And sometimes that happens. And if the moon were, do I have this backwards?
I think
You
so.
do.
Because if the moon's closer to the sun, you see less
Yeah.
of the moon.
Here I'm recording something, I'm gonna look like a moron. Just thinking about a shadow, right? If I have my shadow here, if I put my hand closer to it, the shadow's gonna be bigger. So I think if we move the moon closer to the sun, we should see less of the sun. No, you are right. It's gotta be reversed. I don't know why I'm thinking backwards. But it has to do with the relative position of the sun and the moon together, okay? And so if I change these two, I will see either more or less of the sun. This is actually cool because this lets us see a part of the sun that you would never see normally. You would never in a million years, if you just went and looked at the sun, which you know you should never do, you would not see this part. If we took away the moon, the rest of this is so bright and has such a glare that you wouldn't be able to see this part. This has fascinated scientists for thousands of years. Let me show you this next one. What do we have here? Another eclipse. And you can see kind of here, these little, what is that?
Those are explosions off the sun, right?
Yeah. Yeah, we've got like these solar flares that are happening. And again, these are happening all the time, but you can't see them, right? You can only see them during an eclipse. And so what's happening in this kind of eclipse is that you're able to see the chromosphere. They call it the chromosphere because of this color, because it puts off a distinct reddish color that you can't see at any other time. So, by the way, we're going to begin our study of astronomy with our star. Okay, astronomy would cover our solar system. It would cover the entire universe. The way the courses are broken down in the state of Texas are that basically one half would be our solar system, and the other half is the stars. Yes, sir.
Are we going to study other planets?
Like in other solar systems?
Yeah.
If you want us to, we may, but it's not in the curriculum. Okay, but I'm up for a good rabbit trail, always, almost always. Okay, so we are studying the sun. This is actually part of what you're seeing here is what's called the chromosphere, and to a certain extent, maybe you can see what's called the corona. Right? It's more than just a beer. Does anybody know what the word corona means?
Crown.
Crown. Good. Yeah. So the crown of the sun, which extends out so far. In fact, the Earth, by technical definition, is inside of the corona of the sun, and it doesn't necessarily have a fixed shape or distance, right? It can extend out quite a ways, as long as there's solar material that's hitting it, and we certainly have that. So let me go take a look here. We don't need to see all of these, but I do want you guys to see these. There's probably some cool audio that we're not able to see. This is from NASA. Okay, it's a little bit of a time lapse. They're taking pictures and putting them together, and so we're seeing they've got filters on this, right? If we were to look at the sun, you would not see any of this. There's just such an incredible glare with what's going on. But with the right filters, we can see the surface of the sun here. We're able to see the corona here, and look at how this is stretching out these distances. What else do you see as you look at this? What do you observe?
It kind of looks like it's like cracked at those spots in a weird way.
That's a ionized gas is able to escape, right? And where photons, light, is able to just readily escape. What else do you notice? What's the sun doing?
Rotating.
It's rotating. In fact, they say that, oh, by the way, let's get out notes. If you don't have notes out, you're going to want notes. Okay? You don't want to take down some of these things I'm saying. If you don't have them today, let's make sure that we're set for next time.
Can I write on my phone for now? I don't have a notebook with me.
Sure. I doubt in this class, at least not today, there's going to be anything that I'm going to tell you that's not going to be in your textbook. Okay. But one of the things, just as we're observing this, you mentioned that the Earth or the Sun is rotating. It is. It's rotating in such a way that it makes one complete revolution about once a month. Okay. If you are able to see this long enough in all these ways, you'd notice it's really wild. It doesn't rotate evenly. The axis, wherever, it's hard for me, it's not going fast enough on this to quite see it. But essentially the equator of the sun is rotating faster than at the poles. It has this different, and so it's kind of warping and twisting even as it turns, which is some pretty cool stuff. You see anything else here? You know what this is that's like coming out? Let's go to a little bit of that. So here's our question, right? You definitely have to know this by the end of the day. What is a star made of?
Gas.
It's made of gas, okay? Do you know which gas or gases primarily? There's another way of asking you that question. What is the most abundant element in the universe? Hmm?
Hydrogen.
It's hydrogen. Do you know the second most abundant gas in the universe? Hmm?
Helium.
Helium. Yeah. The reason that it's hydrogen number one and helium number two, I guess hydrogen number one is because there's more hydrogen than anything else. And the reason helium number two is because what's happening in a star, it produces all this light and all this energy and all these flares and all this stuff, is step number one is hydrogen gets fused into helium. And so you've got a lot of hydrogen just because that's how God created the universe, and you've got a lot of helium being produced by that hydrogen. So what is a star made of? It's certainly made of gas, right? About 73% of the sun's mass is hydrogen, another 25% is helium. It says all the other elements, including everything that's in you, that are found in a star make up less than 2%. mean, the universe is hugely hydrogen. By the way, you are too. I mean, I know this isn't a biology class, but do you know what you're made of? And don't say hydrogen, because I know we said that, but what molecule are you made up of? What do you consist of? It's water. You are so much water. And what's water made of? What? Two elements. Hydrogen and oxygen. And it's two hydrogens every one oxygen. You're mostly hydrogen. The universe is mostly hydrogen. The stars, the sun, mostly hydrogen. Now, we're studying our sun right now because it's a run-of-the-mill sun. So or a star. As we're talking about stars in general and their life cycles and all this kind of stuff, our star is a great place to do. It's just kind of average. It's average size, it's average mass, it's average lifespan, so it's a great model for thinking of stars anywhere else. You guys feel good on this? Got a couple pencils, I'll give it. You don't need to know this, okay? This is just something to look at. So hydrogen 73%, helium 25%, and then just these little trace amounts of all these others, okay? How do you know it? Do you know that the sun's made out of hydrogen? Why not? Why not oxygen? Not lithium. Yes, sir. You're in astronomy?
Yes, sir.
Tell me your name.
Brian Torres.
Where are you from?
Here?
Yeah.
Yes, sir.
Very good. You live on campus or?
No, sir.
No. All right. So, how do we know what stars are made of? Any guesses? Take a sample? Why can't we take a sample?
Because we die if we aren't close.
Yeah, it's amazingly hot. How hot is the sun? You can make up a number. Huh? Yeah, it's hot. How hot? What temperature does water boil at? 212 degrees Fahrenheit. How much Celsius? 100 degrees Celsius, right? What happens if your cells, if you get to 100, if inside of you get to 100 degrees Celsius, what happens to you?
Blood will begin boiling.
Yeah, you're just boiling like crazy, right? We can't get anywhere near the sun. It's millions of degrees. Millions. I mean, it's just not even close. We cannot take a sample. So how do you take a sample when you can't take a sample? How can I know that it's hydrogen if I can't go get the hydrogen? How do I know that it's so much hydrogen and not so much helium or lithium or cadmium or anything else? How do I know that?
With the waves, the length of the waves.
Yeah, we're going to do something with the light, right? Because the one thing that the light produces that we can sample, or the one thing that a star produces that we can sample, is light. So, let's talk about light for just a minute here. I'll leave the lights off, feels good. What do you know about light?
It's photons.
It's made of photons, discrete bundles of energy. They're energy, they're like these little tiny packets, and they move. And how do they move?
Fast.
They do. Does all light move at the same level of fast? Yes or no? Right or wrong doesn't matter right now. Just give me. I can work with anything. I can work with a yes. I can work with a no.
Yes.
Yes. All light travels at the same speed. It's the speed of light. It's a constant in the universe. Does all light have the same energy? Say no. 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 All light does not have the same energy. But if it moves at the same speed and it has no mass, but it has different energies, how do I account for that change in energy? It has to do with wavelength, right? So, do you know the longest wavelength of visible light? On the Roy G. Biv thing, right? Red, orange, yellow, blue, green, indigo, violet. Do you know which one has the longer wavelength?
Radio?
It's red. Well, radio is longer, yes, but in the visible, it's red, okay? And the shortest, I gave myself away, didn't I? The highest energy is going to be the violet. So now we live in a digital age, and everybody does nobody prints photos anymore or things, I don't think, but they used to. But you got to be able to see. You can't just sit there with chemicals in the dark. I mean, you're going to kill yourself. So you had to have some kind of a light, but you couldn't have enough light to ruin everything that you were doing, and so they would have a red light, because red has the lowest energy of all the visible light. So relatively speaking, red light travels at the speed of light. It has no mass. It does have energy, but not crazy energy. And so what happens there is it goes kind of like this. Okay? When we talk about wavelength, we're just talking about the distance between here and here. Okay? But now if I have violet, it's got more energy. It travels at the same speed. It also has no mass. So it's covering the same distance in the same amount of time. Where is that energy? Because violet's sitting there going like this. Okay? And so the shorter wavelength means it's traversing up and down more, so to speak, right? So longer wavelength versus shorter wavelength, the wavelength corresponds with specific types of light. The longer the wavelength, the lower the energy. The shorter wavelength, the higher the energy. You want to know that. Write that down, okay? Long wavelength, low energy. Short wavelength, high energy, okay? And we can look at the light, specific light at specific wavelengths that's coming off of the sun. And what's really cool is hydrogen puts off very, very specific wavelengths of light, very discrete. It doesn't put off all light. It doesn't put off white light. Neon puts off a very specific wavelength of light. It doesn't put off all wavelengths of light. It puts off a few. Each element has its own signature, is how we say it, okay? And so I'll turn the page here. So if you look up here, this is what's happening here is we're looking at the bright line spectrum of some different elements. We don't have any of the equipment for this here. I wish we did. This would be the time to bring it out. It's really, really cool. But you can take hydrogen and put it in a tube and put electrodes on either end of it and juice it. And that hydrogen will begin to emit light as the electrons flow through it. Well, it consistently emits light at very specific wavelengths. It has particularly a wavelength here and here that you can see that are just, they're like, it's like a fingerprint, man. You will know hydrogen will always look like this. Hydrogen on Earth looks like this. Hydrogen in the sun looks like this. Hydrogen anywhere looks like this. When I see this, I know it's hydrogen, okay? I believe that this one is helium. Notice it's got this huge red line, or yellow line. It's got a little bit of a red, it's got a little bit of a green, it's got a little bit of a blue. That's a characteristic signature. This, I believe, is neon. Notice it's got a lot going on, a lot of little different lights. This one is sodium. Sodium, when you do sodium, you could do it through that, or you do it through like a flame test, maybe in chemistry. I don't know if you would have had that. But you take a little bit of just sodium, not table salt, but just sodium, and you put it on like a stick, and you put it in the fire, and it's going to go yellow. You've had that experience before, whether you knew it or not. 4th of July in America, maybe different holidays at other times, other countries, or New Year's. What do?
The fireworks.
Like fireworks. And they come in different colors, right? It's because different atoms, different elements, when they're excited, release photons at specific wavelengths. And so you get specific colors. So, spectral analysis of light of different elements, right? So when we look at the sun, though, even though it's mostly hydrogen, it's not exclusively hydrogen.
Yeah.
We're going to get different wavelengths from different elements, right? If you take a look over here, this is a combination of two of these. I want you to tell me which two you think it might be.
top one on the right?
Yeah, this one. I want to know, is it a combination of A, B, C, D, E, or F? Which
Combination of C and F.
C and F. So you see this one, and you see this one.
Yes.
Okay. What's a giveaway that this one's involved?
All the lines towards yellow and red.
Yeah, in particular, notice this little line at 650 nanometers. Like that's pretty much dead on, isn't it? No, and that line is nowhere, nothing else has that line. But here it is. Can't miss it. So I know that that's there. What else is a signature?
The fourth,
Pardon?
the fourth one in the first.
This one here?
No, the fourth.
The third one?
No, the fourth.
Fourth.
Yeah, and the third one as well.
Okay. So here I've got a line, I don't know, maybe like 580, 590, right? I've got one close to that here. So just having that line, it could be either one of these,
But it doesn't have.
but it doesn't have these, right? So that's how they determine what light is coming from our sun or from another star is by doing this analysis of this kind of stuff. You're just looking for the fingerprints of different atoms, different elements. Let's try this one here. What do you think that one's made up of?
A and F.
A and F. Okay, what makes you think it's this one?
The blue line and the red line make an appearance there.
Okay, I've got this turquoise happening at like 480 or so, and I've got a turquoise line here at 40. And notice nothing else has a strong, like this has a light one kind of close, but I don't have this bright yellow here, right? So it's not this one. This has to be here.
You see,
And then you said C. Why do you think C?
so there is like not too light yellow one, is the other red over.
Yeah, I got this faint yellow at about 610, and I got a faint yellow here. And here I've got one at what, like 670 or so, and here I've got one at 670 or so. So again, that's how they do that. I'm letting you know right now, you want to be able to do that. Okay? You will see something like this on a test. Okay? When you go to your textbook and you're reading through this chapter, it's going to have a little link that you can click on, and it's going to. I actually just worked through that link and took screenshots to get this. You can literally practice. Okay? So this you want to know, and this is done in obviously in astronomy. We do this in chemistry. We do this in biology. This is how we determine what pigments and things like that are in plants. So most of the elements in the sun are in the form of atoms. When we say that, we mean atoms like versus molecules. So I mean like it's one atom big, it's not 10 atoms big. You're not going to find DNA on the sun. You're not going to find water on the sun. Okay? It says now with a small number of molecules, very small, and all of those are in the form of gases. Okay? Let's talk about states of matter. Do me a favor, unless you're taking notes on your phone, let's keep the phones away, okay? And then after today, let's make sure that we have regular things to take notes with. Most of the elements in the sun are in the form of atoms, a small number in the form of molecules. Those are in the form of gases. Talking about the states of matter. You know?
Gas, liquid, solid, and plasma.
Okay, let's go solid, liquid, gas, plasma. So if I were to have an arrow here, what things could I represent on that arrow? We can do a number of different things. There's a change here as I move from a solid to a plasma. What's changing? Matter's changing? Like how so?
Physical.
Okay. These are definitely physical changes. They're not chemical changes. What's changing about them physically? Not necessarily.
How close the molecules are close to each other.
Okay. Yeah, so maybe distant. That's not going to be true in the core, which is like plasma. You have the right idea. Just like 99.9% of the time, that is true. On Earth, if I have a solid and I have a gas, the solid is tightly packed, the gas is not. But when we get into the core of the sun, it's so tightly packed, but it stays plasma. So, yes, but no. I'm not putting it right now. But the free flow, right? They flow more. Okay, as I move down. Do you know what I mean by that? Okay, so let's talk about water. Talking about water as a solid. What do we call it? Ice. Do those atoms, I mean, they move, they vibrate in place, but do they flow? No. How about in the liquid? We call it water. Do they flow?
Yeah.
Yeah, they do. But can they flow just wherever they want? No, they're confined usually by a container or something like that. But when I put water into a gas, what do we call that? Steam. Okay. Are they free to flow anywhere at that point? Yeah. Now, you will never find water as plasma. But, and I'll explain why in a moment. But as elements move from solid, liquid to gas to plasma, they flow more. They also have more energy. Okay? Think about water. You sprain an ankle. What do you go put steam on it? No, what would happen if you put steam on your sprained ankle? You wouldn't just have a sprained ankle, you'd have a burned sprained ankle. You'd be dumb. You wouldn't do that, right? It would hurt because you're adding energy. You don't want to add energy. The whole reason you put ice on your sprained ankle is you want to take energy out. You want that heat that's in your damaged tissues to transfer from those tissues to that ice. And so lower energy as a solid than as a liquid, than as a gas, than as a plasma. Right? In terms of their kinetic energy, how much they're moving. Okay? So most elements in the sun are in the form of atoms with a small number of molecules in the form of gases. There are no liquids or solids in stars. Okay? All right. Let's go to this. At least not in ours. You get to a brown dwarf or something like that, the rules change. But for our star, certainly not. It says here the sun is so hot that many of the atoms are ionized. That is, they're stripped of one or more of their electrons. This removal of electrons from their atoms means that there is a large quantity of free electrons and positively charged ions in the sun, making it an electrically charged environment. Scientists call such a hot ionized gas a plasma. Okay, so let's talk about this. There is definitely gas in the sun. There are some molecules in the sun, but most of what's happening in our sun is plasma. Where else do you find plasma?
Fire.
Not fire. Where else? Not in your body, you'd be dead.
Or radiation.
Oh, that's a different kind of plasma. What I'm talking about here when I talk about this kind of plasma is we're talking about atoms that have so much energy that the electrons won't stay around the nuclei. Okay, there's too much. Let's talk about that for just a second, okay? So, in an atom, you get two primary what's an atom made of? Electrons? What else? Protons and neutrons. Okay, where would I find the electrons? Outside. Sometimes it's called a cloud or a shell or an orbital. Where would I find protons and neutrons? The nucleus. So I'm going to draw a nucleus here, okay? Inside of this nucleus are protons and neutrons. Protons and neutrons and electrons, we can refer to them in terms of their mass. We can refer to them in terms of their location, and we can refer to them in terms of their charge. Okay? What's the charge of a proton? It's positive. What's the charge of a neutron?
No No charge.
No charge, it's neutral, it's electrically neutral. It's a charge of an electron,
Negative.
it's negative. Okay, we want to know this, all right? This is fundamental, we need to know these things. If you don't already, you want to know that a proton is positive, a neutron is neutral, an electron is negative. So what's the charge in the nucleus of an atom overall? Positive. What's the charge outside? Negative. Why does an electron go around the neutron or around the nucleus? Attraction, yes. Laws of nature. Opposites attract. I've got these two opposite charges. If I had a negative charge in here, what would happen to this electron out here? It would be repelled, right? In fact, that's an important principle of the shape of atoms and of their bonding is electron repulsion. We're not worried about that. That's deeper than we want to be. But the fact is, this has a positive charge, this has a negative charge. Electrons want to be around protons. Electrons want to be around the nucleus of an atom. If that electron lost energy, because it's going out at a very precise speed out here, okay? If this one in its first orbital lost energy, what would happen? One more time?
You would jump to an internal layer.
Yeah, it would. It has nowhere to go electrically. It would come in closer, right? If it got too close, what would happen?
Explosion.
No, not an explosion. It would crash right into that. And if I put a proton and neutron, or if I put a proton and electron together, what do I get?
A neutron?
I get a neutron. It's called electron capture. This really happens, by the way. And the opposite also happens. You can have a neutron that shoots out an electron and turns itself into a proton. Okay? It's radiation. So, these electrons are moving around at very precise speeds. Now, do electrons ever get excited? Yeah, they do. And you know what happens? They jump to the next orbital. They go further out because they gain energy. And it has to gain just the right amount of energy. And when it does, it jumps out. But it's less stable out there. It wants to come back down. And so when it comes back down, what does it do? If I gain energy to jump out, what do I have to do to come down? I have to lose it. When electrons lose energy because they fall from one orbital to the other, do you know what we call that? Light. They emit a photon of light. That is exactly what happens. Remember I told you earlier that if I took a little container of hydrogen and I jazzed it with electricity, it would begin to produce light, right? That's because I would be adding enough energy for those electrons to get excited, kick out to higher orbitals, but then they don't want to stay there because that's not stable. They fall back down. And when they do, they release light and they're consistent. A fall from one orbital to another for a given element always produces the exact same amount of light. Always. So it's a signature. We can see those things. So, all right. Some basics of atomic structure. We've got electrons out here. When they fall, they have to give off energy. They always give off energy in the form of light, in the form of a photon is what we call it. Okay. Always, always, always. This is how everything works everywhere in the universe. If they absorb energy, they've got to kick out to a higher level, right? What if they gained crazy amounts of energy? And what if the environment was so energetic that all they were ever doing was gaining energy, they couldn't lose it? What would that be?
They hit the things, right?
Yeah, they would. And you know what? You couldn't even have regular molecule. You couldn't have molecules. You couldn't even have regular atoms because with that much energy going on, and this is what's happening, certainly in the core of the sun, is you got your protons, right? You got your neutrons. You might have protons and neutrons. You might have something like helium, where you've got like a proton, a neutron, a neutron. You might have a nucleus, but there's no way, there's so much energy, you can't keep electrons running around it. Helium should only have how many electrons? Say 2. Say 2. Yeah, because I got 2 protons, right? So I should have 2 electrons. But there's so much energy that these electrons can't stay around it. And so they're just whizzing all around like crazy. So when you have a gas, but the electrons have been stripped from the nuclei, we call that plasma. It's got so much energy you can't keep the electrons there. Okay, and that's what this says. The sun is so hot that many of the atoms in it are ionized. An ion is when it's a nucleus has lost its electron, okay? But they're ionized, that is, they're stripped of one or more of their electrons. This removal of electrons from their atoms means there's a large quantity of free electrons and positively charged ions in the sun, making it an electrically charged environment. Scientists call this hot ionized gas plasma. Write this down. What is plasma? I'm just telling you right now, you have to know that. What is plasma? You must know it. What time are we out of here?
1:15.
50. I'll set the timer. Otherwise, I will just go and forget. So, what is plasma? How is light produced? You got to be able to answer that question, right? You know, when an electron falls from a higher orbital to a lower orbital, it emits light, or it emits a photon. You got to know that. What's the sun made of? Hydrogen, mostly, right? And some helium, and the hydrogen exists as plasma. These are some things that we got to know. Okay. How do we know what a star is made of? We look at the light, right? We analyze that light. These are things we got to know coming out of today. You all feel good on this page? In the 19th century, scientists observed a spectral line at 530 nanometers in the sun's outer atmosphere called the corona. They'd never seen this line before. Let me go back to our spectral analysis. It said at 530, right? So let me... .530 would be, you know, like right about here. So it's going to be green. They've never seen this before, ever. Okay? But okay. So they thought they had a new element, so they named it chromium. That's because they saw it, I'm sure, in the corona. And but it was not a new element. What happened was they'd never seen this occur before. There was iron that had lost 13 of its electrons, which is a huge number of electrons. It's wild. The only way that can happen is because there's so much energy in that plasma. And so it was just emitting this color that inconceivable on Earth. So we first discovered that the sun's atmosphere had a temperature of more than 1 million degrees. If you want to know, well, how does that equate to that? That goes into calculus. So they're working backwards from known quantities to derive that quantity. Layers of the sun. This you must know. Okay? You must know. You're going to want to draw it. You're going to want to write it down. You begin with the core. then the radiative zone, then the convection zone, then the photosphere, then the chromosphere, then the corona. This is simply supposed to be like a little cutaway of what's happening way out here. Notice that almost, yeah, well. By the way, we've never seen anything happening in here. We've never seen the convection zone, the radiative zone, or the core. What else sometimes looks a little bit like this? A diagram like this. Y'all ever see anything like this?
The stratosphere.
Earth. Earth often, if we were to do a diagram of Earth, it has a core. It's got some layers to it, right? You go core, mantle, crust, right? Then you have these layers of the atmosphere, troposphere, stratosphere, things like that. So good on this? Core, radiative zone, convective zone, photosphere, chromosphere, corona. We're going to look at detail of these layers here in just a second. Very typical of me to either ask you to draw this and label it, or I'll draw it and I ask you to label it, okay? So just know that. This is like, you've got to know this for sure. There's a graph that'll come up later in chapter 1, and I'll tell you, you must know this. And on that one, what'll happen is I'll give you the graph and you've got to label it, okay? All right. This is the same thing, it's just a little different picture. I thought the other one was a little easier to work with, but it's showing these principles. So one thing that's cool about this is it's kind of showing the radiative zone. So to radiate means to emanate forth. So this is radiating energy, it's sending out energy, whereas this is called the convective zone. You ever heard the idea of convection, like a convection oven? Something like that? What happens there is, as something has energy, it moves up, but then as it moves up, it cools down, and when it cools down, it falls back down, and so you get this activity that happens. Go like this. Human, do it. Do it. Everybody, come on. This is convection, okay? Whereas radiation is just like, pew! And life is better with sound effects. So, the sun's layers are different from each other, and each plays a part in producing the energy that the sun ultimately emits. We'll begin with the core and work our way through the outer layers. So the core is extremely dense. I mean extremely dense. It's plasma. It's got tons of energy. Things are free-flowing, but it's amazingly, amazingly dense. I think I've got a graphic for it here in a minute. This is the ultimate source of all energy, because what's happening in the core is nuclear fusion. We're taking predominantly hydrogens and combining them together ultimately to form helium, okay? And that releases a lot of energy. And it causes everything that happens in all the other layers, and it causes that energy to ultimately make its way out to Earth and beyond. So, you need to understand that the source of energy is fusion in the core, okay? Make sure that you've got that. core has a temperature of approximately 15 million degrees Kelvin, which is also the same as 15 million degrees centigrade because they're only 273.15 degrees apart. It is the hottest part of the sun, okay? All right. Next is the radiative zone. It's its name because it emanates that energy, it radiates that energy out. I come from Las Vegas. That's where I was born and raised. Las Vegas is famous for some very interesting things. One of which is people like frying eggs on their cars or even on the ground. Is a thing. It's weird, just to show how hot it is. One of the things that happens in Las Vegas is that sometimes it can feel hotter at night than at day. Like you can be out walking a street at night in Las Vegas. You're like, where is this heat coming from? The sun's not out. The air isn't as hot as what I'm experiencing. Where's that heat coming from? Well, the asphalt below you has been absorbing heat all day. It's just being pounded by the sun. The sun goes down and now it's, not that it wasn't doing it throughout the day also, but it's radiating that heat back out. By the next morning, it'll be cooled back down, relatively speaking, right? But it's just wild how those things work. So it's the idea that this thing has an energy source, it's just being bombarded with it, and now it's releasing it. Because remember, did I use the word entropy before? Earlier in the day? I talked about the second law of thermodynamics, right? Everything goes from order to disorder, from high to low concentration. Did I say that? Okay. That's entropy. And everything does this. Heat does this. Energy does this, right? I talked about putting ice on your ankle, right? The energy, the heat needs to flow. What does it flow from? What does it flow to? In your ankle situation. Flow from your ankle to the ice. And what is it? The energy moves to the ice. Now what happens is that solid ice, it becomes liquid, right? As it gains that energy, it has a state change, okay? So what's happening here is you've got this incredible source of energy in the core of the sun, and it's heating up that next layer, and it's just radiating it out. And that brings us to don't write all this down, let's talk about it. The light generated in the core is transferred through the radiative zone very slowly. Super high energy, crazy high energy. You can't even have atoms existing in there because it's got to be plasma because there's so much energy. Why is it moving so slowly? Why does light seem to be moving so slowly through this? Anybody here run? Is it hard to run when you're the only one on the track? I mean, like, are there obstacles? What, is there anything that keeps you from running as fast as you can when it's just you on the track? No, there's nobody there, right? But if you were to run at the start of a marathon, can you run full speed at the start of a marathon? No, because there's people all around you, right? And they're going to impede your progress. Does that make sense? No, maybe, okay. If there's nothing in my way, I can just, right? But if there's stuff in my way, then I can't just, that's what's happening here. The light, the energy would like to just flow, right on out, but it's actually going very slowly just because it's so dense, because there's so much packed in to a tight space. So even light moves very, very slowly. It's still, buzzing around, but to get across that thing takes forever because it's constantly bumping into things. All right. Then the convective zone, remember that's this. So it's getting energy from the radiative zone. It wants to continue to just shoot it out, but it cools down as it travels, and then it falls back down. So the plasma heats up and falls, and heats up and falls over and over and over again. The classic one for this is like boiling rice or even oatmeal or something like that, and you see it rise and then it falls, and then it rises and then it falls, because it heats up and then it cools back down. Those first several layers of the sun, you have never laid your eyes on, nor shall you. There's such density there that you can't see them, right? So, what were my first couple layers? Core, followed by radiative, followed by convective. If I wanted to draw a little symbol for the radiative, what should it look like? What was it doing? Yeah, it's just kind of going like this, right? How about in here? It's got to have like a cycle, right? Heats up, it rises, gives off energy, it cools, falls back down, over and over and over. That is what convection is. That's what a convective zone does. All right, now we're into what we can see. The photosphere is the layer where the sun becomes opaque and marks the boundary past we cannot see. So it's opaque, in other words, you can't see through it right here. I'm going to draw a little tiny thin layer, right? It's way thinner than this. I'm going to call this the photosphere. Let's check your Greek. What does sphere mean? It's a sphere. Perfectly circular in all dimensions, right? What does photo mean? Light. So this is the light sphere. I'll write it over here. Maybe. Okay. All right, let's go to the next slide. So this is a picture of this photosphere. We can see it. We can't see in past it. What do you see on it? What are those? Looks like a disease, doesn't it? Or something. It's got a moldy sun or something. How would you describe those spots?
Like holes in the sun.
What holes? What else?
Broken.
Looks broken. Okay. What else? Okay. More details. You witnessed a crime, the officer comes up to you and he goes, "Hey, what'd the man look like?" And you're like, "Well, he looked like a guy." Can you help me out here? You know, oh, he had a beard. Okay, well, what is it? A full beard? Was it a gray beard? Was it a thin beard? Was it a thick beard? Was it a scraggly beard? Was it gray? Was it brown? Was it red? Did he have earrings? Did he have one earring? Did he have 5 earrings? Did he, you know, like, what do you see? Tell me what you see. Okay, looks like rocks. What else?
Splotchy.
Splotchy. All right. What colors do you see?
Yellow.
Yellow. What else?
Brown.
Brown. What else?
Orange.
Orange. Is there any relationship between the yellow, the brown, and the orange?